Okay, Assalamu alaikum, welcome back. We are continuing our discussion of the fine-tuning of the Higgs boson. And we had left off on the verse from Surah Al-Ahqaf talking about how the universe has been created with an inner truth. And in my readings and discussions, I have found that most physicists do seem to subscribe to this notion of an inner truth, whether or not they are religious. And that inner truth seems to be very closely tied up with the concept of beauty. Physicists are, in some sense, enamored of and obsessed by the notion of beauty in the universe. And I think very often that is what is motivating them to study physics and to do their research. And this is very nicely expressed in the book A Beautiful Question by Frank Wilczek. He is a physics professor at MIT. He is a Nobel Prize winner in physics. And one of the questions he poses in this book, talking about the search for beauty in physics, is the world a work of art? And that is how deeply this concept of beauty runs. And in fact, there's a story I remember about a physicist, I believe his name was Hermann Bondi, who showed Albert Einstein a theory he was working on that was actually quite predictive, quite successful in making predictions. And when he showed Einstein the equations, he said, Einstein looked at me and he said, but the equations, they're so ugly. It is so ugly. And Einstein very quickly lost interest in the theory uh, because there is a deep-seated belief that the grand design of the universe at heart is beautiful. And to me, that is very closely tied up with this notion of the inner truth. It is a supreme beauty that in a great sense is not subjective. It is an objective beauty that the observers agree on. But what do physicists really mean by beauty? So very often it is linked to uh, a concept known as symmetry. And this is very nicely expressed by this quote from the physicist Michio Kaku, uh, who says in his book Hyperspace, when physicists speak of beauty in their theories, they really mean that their theory possesses at least two essential features. Number one, a unifying symmetry, and number two, the ability to explain vast amounts of experimental data with the most economical mathematical expressions. And so we find in physics that the notion of beauty is very closely tied into this idea of symmetry. So now let us talk about this concept of symmetry. And this is very interesting because when we study physics in high school and maybe a first-year physics course in college, nobody really talks about symmetry. But it turns out that symmetry is at the foundation of physics in a way that unfortunately just does not come across until one gets really, really deep into physics. But I'm going to try to bring some of that across. And you can see here just a couple of book titles, and we'll look at some more later. Again, just trying to make the point that symmetry is foundational to the modern conception of physics. So here's a book called Symmetry and the Beautiful Universe, again tying in that notion of beauty and symmetry. It is by Leon Lederman and Christopher Hill. Leon Lederman is another Nobel Prize winner in physics. And here is a book called Physics from Symmetry by Jacob Schwichtenberg. And in it, he really goes through and shows how we can derive the various theories of physics that seem entirely unconnected, like gravitation and electromagnetism and all of these different equations that we learn as separate bits and pieces in our first physics courses, that they all arise from this notion of symmetry in physics. And again, just to keep pressing the point home, here is an article called Symmetry, A Key to Nature's Secrets, again talking about how symmetry is at the foundation of physics. And this article is by Steven Weinberg. And again, Steven Weinberg is yet another Nobel laureate in physics. So you see how all of the heavy hitters are stressing the concept of symmetry at the heart of physics. And pretty soon, we're going to take a more careful look at what this symmetry means and is, and how it ties into kind of our spiritual conception of the verse I was talking about from Surah Al-Ahqaf that talks about an inner truth at the heart of the universe. So we're all pretty familiar with the idea of symmetry being tied to beauty. People talk about beautiful faces as being symmetrical. We look at works of art in terms of symmetry. We have a certain symmetry in beautiful works of music and so forth. And we also have a pretty good idea about geometrical symmetry. One type of symmetry, for example, is rotational symmetry. So a square looks the same if you were to rotate it by 90 degrees. And it has reflection symmetry. If you were to divide the square along this line and transpose the top and bottom half, it still looks the same. If you were to divide it along this line and transpose the right and left half, it looks the same. If you were to divide along a diagonal and exchange these two pieces, it looks the same. And these sorts of symmetries also occur in other shapes. Now, when we have something like a circle or a sphere is very interesting because they have a continuous rotational symmetry. If you were to take the square and rotate it only by 30 degrees, it would now look different. So we would call the rotation a transformation. And the square would be invariant. It wouldn't change if you rotated it by 90 degrees or 180 degrees or any multiple of 90 degrees. But if you rotate it by something different, then it would look different. If you rotate it by 45 degrees, for example, it would end up looking like a diamond and not a square. A circle, whatever degrees you rotate it by, will always look exactly the same. It will not change if you rotate it by 10 degrees, 20 degrees, 713 degrees, it doesn't matter. So a circle is completely invariant under rotation, as is a sphere. Again, completely invariant under rotation. And so what physicists mean by symmetry, and this is the critical definition, they look at certain transformations, in this case, rotating something by a certain number of degrees, and ask the question, will it be invariant? Will it look exactly the same? Why is that so critical? Because we want the laws of physics to be invariant under these various transformations. And we're going to explore a little bit more what that means, but we've gone from beauty to symmetry, and now we're defining what symmetry really means. Symmetry means it stays the same. Why is that important? Well, because if I do a certain experiment and get a certain result, and then I move 10 feet over and do that same experiment, I want to get the same result if the conditions are the same. If the only thing that's changed is that I simply moved 10 feet over, that's a transformation. And I don't want the laws of physics to change if I move 10 feet over, as long as conditions are the same, as long as the magnetic field hasn't changed, as long as the electric field hasn't changed, as long as the temperature hasn't changed. I don't want simply the fact that I move in space to make a change to the laws of physics. that, force equals mass times acceleration, but if I move 10 feet to the right, then it equals 1/2 mass times acceleration. That physics shouldn't be that way. Also, if I were to rotate my experimental apparatus, I still want the laws of physics to look the same. If I were to do the experiment tomorrow under exactly the same conditions, I want to get the same result as today. So these transformations in space, these transformations in time, we want the laws of physics to remain invariant under those transformations, and that is what is known as a symmetry in the laws of physics. So again, to drive the point home about how significant symmetry is, I've already shown you a couple of titles, but there are so many book titles in physics about symmetry principles in elementary particle physics, symmetry in condensed matter physics, symmetry in physics, geometry and symmetry in physics, symmetry in physics, and so on. And it is unfortunate that when we study physics at an elementary level, nobody brings across this notion that what seem like totally different physical laws. They say we're going to study Newtonian mechanics, and you study that force is mass times acceleration, and here's how momentum works, and so on. Then we go to electromagnetism, and it's as if we've gone to a different planet. Nobody works to show at an elementary level that all of these different laws are really united in the fact that they originate from an underlying symmetry that has to govern the laws of physics. Now, if you do start to study some physics at this level and with this eye, you will, without a doubt, come across something known as Nothers Theorem. This is due to the mathematician Emmy Noether, who's probably the most influential mathematician that you've never heard of. She was a German woman mathematician and grew up at a time when women were not allowed to study for their undergraduate degrees at the university. She was brilliant in math. And then the most famous mathematician in the world, David Hilbert at the University of Göttingen, finally prevailed on the faculty and the deans to give her a lectureship in math and physics, and told them that her gender shouldn't matter. We are a university, not a bathhouse, and was able to convince them. And she went on to develop something known as Noether's theorem, which really is at the heart of modern physics. And what is this Noether's theorem? What it basically says is that if a system has a continuous symmetry, then there must be corresponding quantities whose values are conserved. Of course, it has, a mathematical form that we're not going to show here. But what this theorem did is it tied symmetries to the conservation laws in physics. I'm sure if you've studied some physics, you remember somebody telling you that one of the laws of the universe is that energy is conserved, the law of conservation of energy. It is never destroyed and it is never created, but it just changes form. And you can use this idea of the conservation of energy to then make calculations about the laws of motion and the speed of a ball as it falls down an incline and all of that. You've probably also run into the law of conservation of momentum. And that's how you can calculate what will happen if two billiard balls strike each other and bounce off at an angle. You probably remember that from first year physics. But nobody ever tells us, why is energy conserved? Why is momentum conserved? Why is charge conserved? Why can't I just create energy? Why can't the total momentum in a system change? It turns out that if there is some sort of symmetry in the laws of physics, this forces the conservation of these things. That is where these conservation laws arise from. It is because the laws of physics have this symmetry that we have already defined as an invariance. So that is the heart of Nothers' theorem. Now, I don't want you to get the sense in any way that I'm trying to imply that this is something obvious, that when I say this, you go and say, oh, yes, well, of course, now I see that. No, this really is fairly complex math. You have to work with something known as a Lagrangian, which is a formulation of the laws of physics that was due to the mathematician and physicist Joseph Louis Lagrange, that looks at energy rather than force as kind of the heart of action in physics. And just for those who have studied some physics, let me just say it formally. What a Lagrangian is you take the kinetic energy of a system minus the potential energy of a system. And when you integrate that, that forms something called an action. And systems tend to move in the shape or the way or the path that produces minimum action. If this makes no sense to you, please don't worry about it. But what I'm trying to say is Noether's theorem is not intuitively obvious. It was really a breakthrough. And what one can show is that translation in space, asymmetry in space, like I was saying, if I do an experiment and then move 10 feet over and do the same experiment, I want the laws of physics to be the same. That leads to the law of conservation of linear momentum. Translation in time, symmetry in time, invariance in time, these are all the same idea. If I do an experiment today and I want to get the same result if I do the experiment tomorrow, if nothing else has changed, this leads to the law of conservation of energy. So symmetry in time, or time invariance of the laws of physics. We don't want the laws of physics to change from day to day. If conditions change, you can plug those different conditions into the law, but we want the form of the law to remain the same. This automatically leads to the law of conservation of energy. Rotation in space, symmetry there, leads to conservation of angular momentum. And, we can all understand what it means to translate in space, that sort of transformation, moving over, translate in time, do an experiment now, then do it later. Rotation in space, turn my experimental apparatus or turn the laboratory by so many degrees in space. These are easy to understand. These transformations are, we can conceive of those, and we see that they lead to these very fundamental conservation laws that we study I'm looking at angular momentum, that we study in first year physics, and there you would have probably come across also conservation of angular momentum. There are other types of transformations that are more difficult to understand, more subtle, and these are the ones that are at the heart of the laws and rules of quantum field theory. These are known as gauge transformations, and we will try to explain them a little bit in the next lecture, inshallah. And just like I can have a symmetry in time, a symmetry in space, a symmetry, rotational symmetry, if my laws obey something known as a gauge symmetry, so that they are symmetric under gauge transformations, this is what leads to things like conservation of electric charge. You remember in early physics, they tell you charge is never created or destroyed. Well, that conservation of electric charge is because there is a gauge symmetry in the Lagrangian component, in the quantum field theory of electrodynamics, in quantum electrodynamics. So gauge symmetry causes this conservation of electric charge. But what I want to focus on here is the idea of symmetry meaning invariance. What does invariance mean? It means that something is always true. It doesn't change. You look at it this way, you look at it that way, it remains invariant, it remains true in precisely its form. Why is this important? Well, as I said, because these symmetries turn out to be the basis of the laws of physics, and these symmetries mean invariance, and invariance means that something is always true. And we see here again Leon Lederman and Christopher Hill. Again, Leon Lederman is a Nobel laureate in physics, telling us symmetry principles are now known to dictate the basic laws of physics, to control the structure and dynamics of matter, and to define the fundamental forces in nature. Nature, at its most fundamental level, is defined by symmetry. Another quote: there is solid scientific evidence that the laws of physics are unchanging. This unchanging or invariant set of laws is constructed from profound intrinsic symmetries, and they act to express the awesome beauty of nature. So these quotes really tie it together. And now when we return to our verse from Surah Al-Ahqaf, مَا خَلَقْنَا السَّمَاوَاتِ وَالْأَرْضَ وَمَا بَيْنَهُمَا إِلَّا بِالْحَقِّ. We have not created the heavens and the earth and all that is between them otherwise than in accordance with an inner truth. We can now get a glimpse of what this inner truth may mean in the world of science. Invariance implies that something is true. It is unchanging, it is invariant. 2 plus 2 is always 4. That is invariant. That is a truth. Whether it is 2 apples or 2 bananas or 2 cars or 2 people. And so this symmetry and invariance that is at the heart of the laws of physics is intimately linked, in my mind, and God knows best, with this inner truth. Because the truth is true. It does not change. And that is the reflection of that is the symmetry and the invariance in the laws of physics. I hope that this point makes sense, and I hope that it gives a different glimpse and different nuance to this verse in a way that we have not really studied in our introductory physics classes. And then, inshallah, in the next lectures, we're now going to try to take a bit of a deeper look at what does this mean in the world of particle physics. And remember, this is the series about the Higgs boson. So it looks like we've gone totally off track because we were supposed to be talking about the Higgs boson, but now we're talking about symmetry. But inshallah, we will bring it back and tie it together because all of this is necessary background to talk about the Higgs boson. So please join us for the next episodes. Take care and God bless.